My name's Steve Strano. I'm the state biologist for NRCS, Natural Resources Conservation Service in Maryland. A lot of my work involves restoration, habitat restoration work. And so I'll be talking about a project, big project that we've had, and then Kathy's going to talk about some of the findings and the science side a little bit. So first, the Pocomoke River is the main subject matter here, and I'm going to describe the condition of the upper Pocomoke River, talk about some of the alteration of it and the effects of that alteration, and then also describe, give you a little insight into the project itself. So in the early 1900s, they used dynamite back then to blow up a channel and drain areas to try to get better drainage. Then in the 1940s, the Civilian Conservation Corps did channel straightening and dredging of the Pocomoke. And within Maryland, the Pocomoke goes up into Delaware, but within Maryland, they actually shortened the channel length by at least 4 miles. They put the dredge material, which was a lot, in addition to channelizing it, straightening it, they also dug it deeper. And all that extra material, they threw up on the bank, pulled it back a little bit, and then the rest of it went in these giant, sort of unmanicured piles along the sides. And then in the 50s to 70s, thank you, Soil Conservation Service, we assisted with all this public drainage and put in tax ditches and that whole system, which added a lot of drainage. Now, before the 1940s, there was still a lot of agricultural drainage at the field level. There was, in fact, a real lot of that, but this really gave this fast sort of drainage where the water can move through the system extremely fast. And this is actually a picture from when it was done. And really, besides the fact that now there's big trees all along this bank and back along the spoil here, it looks pretty much the same. You can see that big spoil levee there. This is what it looks like today. You can't really see here, but there's a spoil levee that's about that elevation. The river here is up pretty high too, so that water can't get back there. This is the other side, the back side of that levee, about 10 feet tall in this location. I'd say typically you're talking 5 to 6 foot height, but it really is highly variable. On the tax ditches, lots of times they put some fill on here so they make it easier to ride along the right-of-way and do the mowing and maintenance. And then you'll see the spoil either right on the edge or sometimes it's back in the woods, just inside the woods. So this is a digital elevation model using LiDAR, showing lighter colors higher in elevation, darker lower in elevation. And from Route 50 down to the end, and you can see the purple line is the channelized portion of the river, and that light blue line is actually the old channel. You can see there's a lot more meanders going on. This is up in the headwaters at the Maryland-Delaware state line, where the Pocomoke actually branches off up here. You can see the same sort of thing, where the old channel meandered much more, but you can also see in this, you can see like the tax ditches, and then if you look at closely enough, it's a little tough maybe, you can see all the field drainage, agricultural field drainage in this area. And this one, it's maybe even harder to see, unfortunately, but you can see the channel. Here's the floodplain, right? And here's the channel. And then on each side of the channel, you can actually pick up those spoil levees. There's slightly lighter areas that run parallel to the channel on both sides. So in a close-up, you can actually see what the elevation difference is. I think it's about 5 feet of elevation here between that spoil levee and the floodplain. And you can also see there are some small natural breaks in it in places. This is the historic channel. So I think if you actually measured that at a much larger scale where you're zoomed in, you'd probably be even more distance that was lost in that channel length. And this is a little side ditch drainage that comes in, and this is some ag land that is up probably 5 or 6 feet above the floodplain elevation. So we've got this disconnected floodplain. It's disconnected from the river by those spoil levees. And what do you get when you have a disconnected floodplain? And this is not the only place we've heard about this, out the Mississippi River, where they actually built levee systems, the Army Corps. We got the same type of situation. Well, when a storm event comes through, the water it has to go higher to get out of the system before it can spread out in that real wide floodplain. So you get higher river stages as a result. Higher river stages also mean more velocity of flow because you have less contact with a rough surface that will slow the water down. Floodplains function to retain nutrient and sediments, so if you're not getting water into the floodplain, you're losing that benefit. You do lose some flood storage because the water can't get out, the river stage is higher, so now you're going to get some more flooding potentially downstream of some urban areas, roads, crossings like that. We're also losing some of the hydrology that supports a wetland ecosystem. So the surface is not staying as wet, and therefore you don't have the full ecosystem functions that it naturally would have. And you actually lose some elevation sometimes too. These systems store a lot of organic matter because when organic matter, leaves and branch and everything are saturated or inundated, they don't break down as quickly. And that's how you get peat buildup and muck. Without the flooding and with a lower groundwater table, you do wind up losing that. It oxidizes into the atmosphere and the surface actually subsides. And sometimes you actually get too much flooding. You get water behind the levee, not from the river, but from the adjacent watershed that drains directly down into the floodplain. And sometimes that water just can't get out because of the levee. So this is an image of some trees that are propped up about a foot off the ground. This is where we lost organic matter and lost about 12 inches in elevation in that floodplain. And this has been documented with like 30 years of monitoring of a site right on the Pocomoke. Of course, you get some downstream flooding potentially. Snow Hill is one potential candidate for some flooding downstream. I mentioned a reduced hydro period, or not as, becomes a drier floodplain than it naturally would be. And what you see here is some nice big old bald cypress, but the soil is sort of brownish. It's not that black, mucky soil that you would expect to see if it's getting a lot of flooding going on. So this is going to be a series of illustrations showing what we have now, which is spoil levees on both sides of the river channel, right? And your floodplain back here somewhat disconnected from the channel. You get a storm event, and the water rises in that channel. But it really has to rise high to get out. Sometimes it does on the Pocomoke. Sometimes it overtops those levees. But lots of times it doesn't. Sometimes, as I mentioned, you get water coming off the land surface adjacent to that floodplain, and then you get a higher water surface back here than you have in the channel. Now, if you remove those levees, now when you get a storm event, as soon as that water gets up over that elevation, it can start to flow into that floodplain. And then when that water recedes, it drops down, and some of that water gets trapped back there. And then it slowly filters down through the soil back into the river. but it's a slower process going through the ground than just flowing over the surface back into the river. So when you do reconnect these floodplains, the benefits that you should get out of that are floodwater storage, nutrient sediment retention. In this particular case, because pretty much all of the Pocomoke floodplain is forested. There's a few spots that aren't, but most of it is all forested floodplain. When we do this type of work, we're actually not taking any agricultural land out of production. Most of it, the Pocomoke floodplain is too wet anyway to really farm. So that's an added benefit. We're going to store organic matter again because we're going to make it wetter and get more organic carbon stored. And during those summer storm events, particularly, if we can get that water back in the floodplain, when it drains through the groundwater slowly, it adds base flow to the stream system. So it could increase the amount of flow you have during the dry times, which is good for the fish and other aquatic organisms that are in there. So this is sort of what a natural bald cypress swamp should look like. Dark, mucky soil. These are some nice big 5-foot deep diameter cypress. And there are some of those down the Pocomoke still. Just some of the creatures that benefit from that wetland floodplain ecosystem. That feed on the insects and the amphibians that are in there. This is a graph of the peak storm events on the Pocomoke River at Willards, in Willards, Maryland. There's a gauge station there just where the Route 50 crosses the Pocomoke. And you can see the peaks from 1952 up to about the 1980s were all fairly low. And then you hit that period and all of a sudden you started getting these really flashy, like giant peaks. And that period before is when we were putting in a lot of that public drainage. So it does suggest that, when we were putting in all that drainage, we're essentially short-circuiting the system, converting it from a groundwater-dominated system to a surface system where the water moves faster off the landscape. This is different years of the flood stage at that same station. And this is the floodplain elevation there, and this is the approximate spoil levee elevation at that same location. So if the water goes up to this point, it's not going to get over that spoil levee. There are a couple storms that got up high enough to get over that levee, but there's a whole lot of storms in there that won't get over that levee the way it is now. The phosphorus and nutrient, the nutrient retention and sediment retention has been looked at by researchers over the years. And this is essentially showing that the isolated or your channelized systems with the levee are not retaining nearly as much phosphorus as a natural system without the levee is retaining. So there's big potential gains for phosphorus retention. And the same really goes for sediment and nitrogen too.
So is that probably sediment-bound phosphorus?
Yeah, a lot of it is sediment-bound phosphorus, yes. Kat will talk a little more about that chemistry later on. So within Maryland, the main stem Pocomoke has about a 4,200 acre floodplain that is partially disconnected from the river channel itself. 14 miles of dredge channel and 28 miles of spoil levee, essentially both sides of that channel has spoil levee. So how do we do floodplain reconnection? Well, we want to install breaches in that levee to allow that water to get into the floodplain more frequently during storm events. we're not talking about a lot of smaller storms. They're only going to get up so high. So it's more about those length of the breaches, how long they are. So the longer they are, the more water you can actually get to flow into the floodplain. We do need to be careful about where we put that material when we remove it, the spoil. We don't want to pile it up and create an even higher levee somewhere. So we try to be careful about not piling it any higher than an existing levee. So the water doesn't have to go any higher to get over top of it. And we also, as with all our projects, want to make sure we're not flooding someone's lands that shouldn't be flooded. And that's always a concern to us. So we have this project along the Pocomoke, and we started with this area, which is close to Whiten Crossing, if anybody knows that. Snow Hill's down here. That's where it was first channelized. That's the end of the channelization, up to Route 50. And now we have a new section we're looking at between Route 50 and the Delaware state line. The LiDAR data, that digital elevation model, really allows you to look on a large scale what is on the landscape and where are these areas that have been changed and altered. And we took that LiDAR information and plotted out, here's the floodplain boundary, right? There are roads that cut through it, PDA tactics that come in. Two light blue lines that are parallel are the spoil levees. So you can see there's spoil levee all the way up and through this system where it's channelized. Took that information and overlaid it with some tax parcel information and also identifying where different natural and also artificial boundaries were along that floodplain, like road crossings and stuff. And so that allowed us to figure out what areas can we open, put breaches in and not affect any other portion of the floodplain. As a result of that analysis, we came up with this crazy map, but also came up with about, I think it's 20 floodplain restoration units. So 20 different units that we can do restoration on, and not, if we just do it on one, we're not going to affect the other 19. So we're not affecting lands where we don't have people who are willing to participate. That's the main thing there. Within that original project area, that southern portion, we have about 3,400 acres of floodplain. There are 65 tax map parcels. Some of them were the same owners, but it's a lot of landowners. We had a good amount of state-owned land and some city-owned land too. Town of Berlin owns a lot of property there. But we still had 49 parcels that were privately owned and 2,100 acres. So we really needed that private lands participation. What you hear with the Farm Bill, how important private lands conservation is to water quality and just conservation in general. We have 42 parcels participating now, covering 2,600 acres of floodplain, and we've restored 2,200 acres to date, or at least partially restored 2,200 acres. The other nice thing about the LiDAR, it's great on that large scale, and then when you zoom into it, it's so detailed. I mean, you essentially have an elevation, land surface elevation point for every square meter of ground surface. You could survey out there all day with a survey crew. You'll never get that much information. So you can actually design off of this stuff. You do need the ground truth, but you can design off it and figure out where your breaches should go, where maybe are the low spots where water will be more likely to come in, and where you can put your spoil and how high you can put that spoil. You can see the spoil levee there. That one on that side is higher than this spoil levee here. So this is some of the construction. Got an excavator out there digging through the spoil levees. And you can see here, that's where it hasn't been dug through, and this is the breach here with some jute matting for stabilization, and then we seed it. This is later on after it's been stabilized and the leaves have fallen, and you can see the river channels right here, and this is the floodplain area. And when you do a storm event, you can get some flow. Here's the channel over here, and this is probably about a foot depth of water moving through the system. That was, I think that happened within about 2 weeks after we finished it, which is why you still see the jute mat there and stuff. This one looks like, hey, this never stabilized like this guy did, but that's actually, all that light color material is sand that has dropped out from the flooding. So as that water moves across that breach, heaviest materials are going to drop out first. And then as it goes back in the floodplain, you'll get the silts and the clays dropping out and organic matter. And just another picture of a breach from across the river. Here's another breach from a high perspective, and you can see that's the breach there completely flooded with water flowing across it. Another breach that's completely inundated, you know, you can't even tell where the breach is except you see the mounds over here. And you can see how high that water can get. I mean, that's a few feet up on that tree right there. When we get on the Public Drainage Association ditches, which, you know, they have right-of-ways, they need to mow, maintain those. We want to make sure that their heavy equipment can get across those things without sinking down into it. So we've been using this cellular confinement material and backfilling that with a 50-50 soil stone mix. And that can handle, you could have tractor trailers running along that stuff. It can hold up to it. Because it's a three-dimensional grid, it really has a lot of structure. And just a couple more breaches. This is a breach on a tax ditch. Another one here on a curve of a tax ditch where the water can flow back in. And picture of my truck on one of the breaches. And just the last slide here is just showing, we weren't the first ones to think of this. This is from June '82. This is DNR, actually Soil Conservation Service, and DNR had a similar illustration to what I showed. Here's before and the after where you remove some of those levees. So it was thought of a long time ago. We just have some of the conservation funding that we can actually put to actually implementing this now. And these are the partners who've been working on the project. And now we're going to switch speakers.
I have a background in hydrology and watershed modeling, and Steve set me up well. He gave you a good overview of our work in regards to implementation of these projects. I'm going to talk about monitoring the outcomes of these projects, right? So a big question always is, are we measuring the benefits, the water quality benefits of these wetland restoration practices? So there's a couple of ways we can go about trying to answer that question. One, we can kind of take a modeling approach, right? We could take the Bay Program model, for example, use their assumptions about the size of the wetland, what's being delivered to the wetland, and come up with an estimate of how that wetland is functioning in the landscape. We did that for all the wetlands in the Pocomoke River watershed, and we found that the floodplains tended to have a higher retention capacity for nutrients and sediment than headwater and stream restoration types of wetlands, which is what drew us to those floodplain restorations. But we also recognized that relying on that kind of median might not be the best way to target or to place practices on the ground where we can get the biggest return on that investment. So that's kind of floating in the background. Another way that we can estimate the benefits is we can really take advantage of that LIDAR data to evaluate the volume of water that we think is spilling into that adjacent floodplain. We can look at the chemistry of that river water and combine that information to come up with an estimate of how much nutrients and sediment are spilling into the floodplain area. Now, there's two major assumptions underlying that calculation. One is, are we is that are those overbank flood events occurring as frequently as we expect them to on average from one year to the next? And the second major assumption is that river water is spilling over and filling up the entire floodplain, if you will, right? That it's the primary source of river water to that reconnected floodplain system. So unfortunately, we really can't take advantage of some of the precision agricultural technology that might enable us to look at soil moisture conditions and get a really good detailed information about ground conditions there. We kind of have to take more traditional point measures and try and build evidence or build confidence in those assumptions that we're using to estimate the benefits of these floodplain reconnections. So what I'm going to talk about today is some of the work we're doing to try and dig at those assumptions. So one question, first I'm going to focus on, do these floodplain reconnections restore the natural hydrology? Yes, but it's complicated. I'm going to give you the punchline as well. The second question is, do river waters contribute directly to that floodplain water budget? Yes, in part. It's complicated. And thirdly, can we take direct measurements or see direct evidence of increased sedimentation and increased nutrient retention in those wetland soils as we expect them to function? And that's really work by USGS that I'll get a chance to touch on toward the end of this presentation. So that first question. The way we tackled this is we first took a look at the gauge data from a USGS gauge station that's located about halfway along our floodplain restoration project area. And we looked at the stage data, the river height, in comparison, which is in blue, in comparison to the floodplain elevation, which is in green, and the levee elevation, which is in brown. And what you see for this year, 2015, is that there were 5 or 6 events that exceeded that floodplain elevation, but did not overtop the levee, suggesting that none of those events, waters from none of those events were reaching those floodplain areas and leading to inundation as we would expect them to do in an otherwise naturally connected system. We looked also at a longer time series from 1990 to 2015, and we found that on average, each year there were 5 to 6 overbank flood events that we think would normally, under natural conditions, provide waters to those floodplain areas. But with the levees, those overbank events only occur once every 2 to 3 years. So here's how we expected the role of restoration to come into play. We're expecting that the reconnections will help restore the natural hydroperiod of these floodplain wetlands. In other words, with those floodplain reconnections, we'll start to see more frequent flooding events, higher water table conditions, and longer durations of flooding because of that more natural connection between the river system and the adjacent floodplains. As opposed to these disconnected systems where only the extreme events are overtopping the levees, and otherwise you have a rather disjunct or separated connection between those floodplain areas and your river system. So how did we, let me just back. The other point to make is we recognized that it would be really difficult to restore that natural flow regime. But we did expect the restorations to provide some medium condition between that channelized condition and that naturally connected condition. So we worked in 5 sites along the Pocomoke River watershed. The Pocomoke River watershed is about 450 square miles. We worked in 3 sites along the main stem. Furthest north is a channelized site. And then just south of that is a restored site. And then we have our naturally connected site a little bit further downstream. We also had 2 plain restorations along smaller tributaries to the Pocomoke River proper, 1 restored and 1 channelized. And across all sites, we collected water level data in addition to local precipitation data and river stage data. So just to give you an idea of what a site setup looks like, here's one site where we have a network of wells across that floodplain area. Within each well, we have water level loggers that are recording water levels hourly. And then from those logger deployments, we have hydrographs for all the points within that wetland complex. So I'm not going to make you study those hydrographs. I'm going to jump right to a table summarizing the logger data in relation to those hydroperiod characteristics I highlighted earlier on. So if we look at the mean depth, of the blue is the naturally connected system, the reds are the restored systems, and the green at the bottom of the screen are the channelized systems. So let's first look at the mean flood depth. You can see that it's highest in the naturally connected floodplain, ranging typically around 20 centimeters above the land surface. In the restored sites, we have an increased flooding depth relative to the depth we saw at one of our channelized sites. It's interesting that our main stem our channelized site also had actually a hydroperiod signature that wasn't that distinct from, that it appeared to be kind of more naturally connected than our restored sites. And I'm going to come back to that in a minute as to why we think that's happening. It's also interesting, we didn't really see a big increase in the number of flood events occurring at our restored site. But we did see a slight increase in the proportion of time that site remains flooded throughout the year. Another way that we can look at these data is just to look at the proportion of time that the water table occurred above an elevation relative to the land surface. So in different colors are different years, the project ranging from 2014 in the lightest color to 2017 in the darkest color. On the left is the channelized site, in the middle is the restored site, and on the right is the natural site. And the other detail to cue in on is this vertical line, the vertical gray line, which indicates the land surface. So you can see that in the channelized site, there wasn't a lot of variation between the years, and that the water table typically occurred 50 to 100 centimeters below the land surface. Whereas in the natural, let's go right to the natural site on the right, that water table typically occurred right at the land surface. At the restored site in the middle, we start to see an increase in that water table elevation, and we saw much greater variation among the years with the restorations occurring at this site in 2015. So from this perspective, we're starting to see we're pushing the system more toward a natural flow regime, something closer to what we might expect under a naturally connected system. We also start to appreciate how hard it is to push the system to that natural condition. Okay, next question. Do river waters contribute directly to that floodplain inundation? Here's kind of how we approach this conceptually. Give kind of two extreme endpoints of what might be happening here, right? One hypothesis is that it's the river water that's predominantly contributing to that floodplain area and spilling over. Alternatively, it could be the ditches and the local tributaries draining into the floodplain that's contributing all the waters in that floodplain area. So how did we go about assessing the condition and the relative influence of these local and regional water inputs? This is the densest slide. We took advantage of some detective tools, if you will, that's often used in contaminant hydrogeology, right? So rather than just looking at the nutrients, we looked at the dissolved solids in that water. So they're referred to as the magic 7 dissolved solids because they constitute more than 95% of the dissolved solids in any particular water sample. And they include calcium, magnesium, sodium, potassium, chloride, bicarbonate, and sulfate, alkalinity. And the concentration and the ratio of those constituents can be really helpful to identifying or fingerprinting different sources. So the pattern in which these symbols plot and the relative location of those plots can give you really good ideas for how that groundwater is evolving, how those waters might be mixing, and what might be influencing the water chemistry in your study area. So a couple more details that are helpful to interpreting this plot is you can also get a good indication for how the geology is affecting the water chemistry, but also how human activities might be affecting the water chemistry, as well as any kind of natural biogeochemical processes that might be occurring. So relevant to the eastern shore, natural water samples tend to be a sodium bicarbonate type and fairly dilute, so they would plot down in this area. Samples that are more influenced by agricultural fertilizers tend to have a higher calcium, magnesium, sulfate concentration. So they would plot up in this blue, the top portion of this diamond. And then samples that are influenced by salt water or road salt would have a stronger sodium chloride signature, so they would plot over in this, on the right side of this diamond. And the last detail is that the size of the symbol is intended to give you an indication of the concentration, right? So more dilute samples have a smaller sized, more concentrated or larger size. So with that, now we can start to compare these water samples and get a good idea for what's the interaction, what's the influence. If this was the true case, then all the symbols would plot similarly to where the river water samples are. So the river is in blue. We have minor ditches and small tributaries feeding into these floodplains in the magenta. We have interior wetland samples in green. In the light blue are near stream samples, so samples that are taken just on the far side of the levees or near the breaches. Everyone with me? So here's the takeaway. Focus on the diamonds here. On the left are the results for the restored floodplain, and on the right are the results for a channelized floodplain. First take-home message is to notice the variability in those samples. They are not plotting on top of each other, meaning it's not all river water and it's not all contributing discharge, small tributary discharge to those sites. Secondly, if we concentrate on the restored floodplain, we see these interior areas, these interior samples, smaller in size, kind of more similar to what's expected in the under natural conditions. You also see that strong agricultural influence on the small tributaries coming into the system. Interestingly, the river water plots kind of at an intermediate location of those two potential sources. So this is most likely not direct mixing at that site, but that river water is kind of an integrated signature of the overall Pocomoke River water condition. It's a little bit to the right towards the salt, and we're going to come back to that in a second when we look at the channelized site. So the river water is a mix of these natural waters and these ag waters. The interior water is somewhat closer to the river water. There's some evidence of that river water affecting or influencing those interior wetland samples. On the right, we have the channelized floodplain. And this is very interesting. Again, we have the interior samples, so you can see how highly concentrated these are. You can also see that they're clearly plotting in the sodium chloride water area. So what we realized when we saw these rather salty water samples, we took a closer look at the local contributing area, and this is an area right along Route 50, drains, this wetland is capturing a lot of drainage from road runoff. So clearly, the land use, the land management in that local contributing area is having a very big influence on that interior water conditions. I didn't show the headwater areas. These headwater restorations are in forested areas, and it was really interesting that the local discharge was quite dilute, more natural. There was very limited evidence of human impacts, if you will, on the water quality of those local discharges coming into the floodplain areas. So the last point that I want to highlight here is if we focus on those local tributaries, and let's look at this lower left triangle here, is to notice the variation, the size of the symbols, the range of the symbols, indicating that some tributaries are much more concentrated, much more contaminated, if you will, than other tributaries. And the take home here is targeting is really important, that not all tributaries are contributing the same. There are definitely tributaries, small waterways that are having a disproportionate influence on our regional water quality. So the bottom line is the water quality data suggests that it's not one or the other, but these floodplains are really functioning as a mixing zone between the local contributing areas and the regional waterways. The last question is just a quick kind of thumbnail overview of the work that USGS is doing to actually measure sedimentation and nutrient dynamics in these floodplain sites. And the way that they approach that is in connection with our water table wells. They installed a network of feldspar clay pads, right? So these are markers right at the land surface. You let them sit out for a year, 2 years, 3 years, the duration of the study, and over time you have sedimentation that occurs above these clay pads and gives you an indication for how much sedimentation is occurring across the floodplain site. The other thing that they did is they collected soil samples, and they put these kind of resin bags out. Resin bags are like artificial plant roots, right? You leave those out over 2-3 years. You take them back to the lab, and you can measure the amount of available nutrients that were released over the duration of that study period. So they deploy these sediment pads and these kind of artificial plant root resin bags at the channelized main stem site in the upper left, the restored main stem site in the upper right, the restored headwater site in the lower left, and the natural main stem on the lower right. And you can see from what's really striking is that the sedimentation rates were relatively high across the entire complex of that naturally connected floodplain system, whereas they were consistently lower and much more variable in those connected or channelized systems. And we did start to see some increased sedimentation rates closer to those breaches, which are highlighted here in white, and also along some of the preferential flow paths that are not evident from these maps, but that occur in these floodplain complexes. So we're definitely seeing some kind of pushing towards trying to increase, we didn't see big differences between the restored and the channelized main stems, but we had a sense for the functioning of these altered wetlands in comparison to that natural condition. So that's it. That's the whirlwind tour of trying to assess these floodplain functions, trying to measure these floodplain functions. Are they providing the benefits that we expect by digging at and evaluating the hydrology, the water chemistry, and the sediment dynamics of these systems? So what we found is restoring floodplains is hard, right? It's difficult to overcome the expansive hydrologic alterations. Clearly, the number of breaches, the size of these breaches have a major influence on the connectivity between the river system and the floodplains. These breaches tend to be about 25 to 100 yards in length, and in general, 4 to 10 breaches every mile. So you start to appreciate we're excavating a relatively small portion of that levee that runs along the river system. So if we want to maximize that connection and restore that natural hydroperiod, we really need to maximize the excavation, if you will. Secondly, it's clear that floodplains are providing really important sinks and transformers for the local tributaries as well as the regional waterways. We also saw that the function largely depends on, the influence, the opportunity for these wetlands to function largely depends on the watershed condition, especially in that local contributing area. I didn't touch on or emphasize the importance of watershed position, but clearly upstream to downstream has a major influence on that interaction, kind of that interplay between the local contributing area and the river system. Looking at the water chemistry, the final take-home point that I would highlight is it's clear, based on the variation in the water chemistry, that targeting BMPs is essential. There are definitely waterways that are having a disproportionate impact. These are where we need to get the practices on the ground to reach our water quality goals. And with that, that's the story, and I'll take any questions. We'll take questions. Yes?
Steve might have said, but how do you determine how far down you're going to take the bridges?
They were excavated down to the floodplain elevation. Thank you.